So reading the question to start, matter as well as light can demonstrate wave-like behaviour and particle-like behaviour. So that might surprise you to start with, knowing that you can, what it's getting towards is that you can get these interference patterns from an atom beam. So an atom beam is being fired through a double slit. There's your two spots that it's going through, and it produces an interference pattern of fringes on the screen. Anyway, carrying on, the de Broglie relationship, wavelength equals h over p, where lambda is a wavelength, p is momentum, and h is Planck's constant. They can be verified, so that equation there can be verified by the experimental observation of the diffraction of atoms. In the experiment below, a beam of atoms is incident on a double slit with separation of d, given there. So that's telling you a bunch of stuff that's going to be in the formulas. The question A says, show that the de Broglie wavelength of an atom of mass m is related to its kinetic energy, that's important, by the following expression here. So this is what we're aiming for. It's a mathematical type question. Where does it come from? Lambda equals h over square root 2me. Looks very similar to this equation up the top here that they've given you. So the only difference is that they've arrived at p being equal to square root 2me from somewhere. So where did that somewhere come from? And also a good way for you to start these questions is to list any related formula. So we've already got the wavelength equals Planck's constant over p. We know that p is replaced, so it's a good idea to put the p, the momentum, in terms of a formula, p equals mv. And we're also told it's related to its kinetic energy by the following expression. So kinetic energy appears in there somewhere. Kinetic energy, E, using the term they've got instead of E subscript k, equals half mv squared. And what it seems to me is that we, in fact let me just detail this out in a little bit more detail. This square root 2me term, that does not have v, so v is missing, and p is obviously missing because p equals that, and that is p is missing from this equation. So we've got to, I think, link these two equations together somehow and eliminate the v and the p, and that should substitute into that formula. And the way that I think we should do it, especially to eliminate the v, because the p is just going to be written in terms of these things, so we only really need to worry about the v, is to rewrite the formulas in terms of v. So p equals mv, rearranging as v equals p over m, and ek equals half mv squared, or the kinetic energy equation. That gives us v equal to the square root of 2 e over m. Okay, so that's where the square root comes from, that formula, that's where the 2 comes from. The m's are what we have to worry about now. So equating these two to remove the v from the equation, we end up with p over m equals square root 2e over m. So what do we do from there? We're looking for 2me, so we might like to get rid of that square root just for now. You can do this a number of ways. I'm going to do it this one way. That seems to work for me. I'm going to square everything, and we're going to end up with p squared over m squared equals 2e over m. And you can see that the m's, this m here, we're going to cancel it out and bring it over here. So we've multiplied both sides by m squared. The square cancels with the single m under there, and then we're left with 2em, which you can rewrite as 2me, just to be in the form that the other one is. And rearranging, or not rearranging, getting rid of the square, we take the square root. So we're ignoring this part now, and we end up with p equals 2me, which is exactly what we're aiming for. And then we just substitute into our original formula, where we end up with wavelength equals Planck's constant over square root 2me. And that's the first question done.